Recording in progress. Yeah, no, today I was just, today was just, now we have freaking professor to go on for the next 4 freaking hours. Because
hello, people. Can you confirm that you can hear me? Hi, good job. Everyone here hear me too, right? Okay, so the midterm is next week, right? The first midterm is next week, and it's going to be 1 hour, and we're going to do it in the like 7 to 8. Okay, and it's going to be almost 3 problems, and the plan is to basically have it on the first part, the thermal part, before we move to the heat transfer. So what is the thermal part? The psychometric stuff, a psychometric chart, the humidity and humidification. And before that, we had the mechanical vapor compression to get the COP, refrigeration, COP, heat pump, right? And before that was the Rankine cycle, how we can get power basically from a power cycle with turbine and feed water heater and boiler, right? So that's the plan. And I uploaded for you the exam from last year, including the final, because the final had problems that is related to the thing. I was actually looking at the final from last year grading, because like we have an EBIT, you know, EBIT is the organization or accrediting our program, so that when you get your bachelor degree, you would say this is EBIT accredited. And so they visit every 7 years. When we are doing good job, they only visit if you are a bad school, they visit you so often. But if you're a good school, they just like come and check every 7 years in you. And they tell you, okay, we'll come see you after another 7 years. So I was looking at I was preparing the sample from our work last year. And that final exam problem so the exam last year, the final was 2 hours, and it has only 3 problems, right? It's not like 1 hour C problem, 2 hours C problem. And one of the problem was this big Rankine cycle. And I told them to write a MATLAB file that will simulate basically that cycle. And remember, the exam is open book. They can go and check all the previous stuff that we did. And the average, the exam was out of 300. And the maximum, I was like trying to find what is the best student I have. And the best student was 240 out of 300. So that's like a B, because it's 80%. The A is like 85. So of course, the course had A people because you did good in before, so then that carry you in the final. But The best student in the final exam last year in those 3 problems was B. So I'm telling you, in case you find it a little bit hard, and don't be too hard on yourself, because last year was 2 hours. Those people, basically, the best was 240. There are people who got, what's sad is that there are people who got like 100 and even less, maybe 80 or 70 out of 300. And those are the people, when you tell them just plot the pH diagram, they will be like, they will like plot weird things, right? Or you plot the TS diagram and they'll know what this is. This is very important to be able to plot a cycle on a diagram, DH or TS. That's very important. That's what's going to be on the quiz today. So in the quiz today, I'm just going to tell you to plot things on pH and TS diagram. So it's really important for you to understand, where is the subcooled region? Where is the superheated region? What's on the right? What's on the left? Some people didn't really had CERM 1 last year. They had it like really long time ago and they don't remember. You ask them, what is the efficiency of the cycle? And they're like, I don't know. Everyone should, coming from CERM 1, at least you should remember what is efficiency of a cycle, right? So those are the things that's important for that midterm. How to analyze a cycle, how to analyze a cycle. Get the H's everywhere, and then learn how to calculate work net, how to calculate the Q added. Work net over Q added, that is the efficiency, right? The H is really easy because most of them are like saturated. So you get them from the saturated vapor, saturated liquid, right? And in the vapor combustion cycle, I think what is really hard maybe is the definition of the COP. Sometimes you are confused. Is it Q dot L over work or Q dot H over work? That could be confusing a little bit. But calculating the work and the Q dot, that's as simple as, how do you calculate Q dot H or Q dot L or the work? It's the same formula, which is, what is the work of the compressor? If someone tell you, calculate work dot compressor in kilowatt, what do? You'd say M dot delta H, yes, M dot delta H, M dot H2 minus H1, because we usually start counting from 1, saturated vapor, and then we go to 2, 3, 4, right, on the pH diagram. So it's most of the time it's just like Q dot is M dot delta H, really. Heat exchanger, boiler, turbine, pump, everything is M dot delta H. So get the H, do M dot delta H, get your Q and work, and figure out what does he want. Does he want efficiency? Does he want heat rate? What is the heat rate? Anyone remember what's the heat rate? No, for a power plant. For like a steam power plant burning natural gas and giving you work. And he said, what is the heat rate?
The opposite of
the efficiency, the opposite of the efficiency. Rather than work over Q, it was Q over work, but that's not it. Not just that, there is another complication. It's not just like 1 over eta. What else happened? The units. So the efficiency, when you say the efficiency is work net over Q added, that should be in kilowatt, that should be in kilowatt. The efficiency is 40%, 45%. It's dimensionless. But the heat rate, it's Q over work, but they want those weird units. They want the Q to be in BTU hour. And they want the work to be in kilowatt hour. So what's going on? You just need to convert the BTU to the kilowatt hour. So it ends being 3,412. So the heating rate, and if you just Google this, you'll find out, and again, the exam is open book, and open internet, you can just figure what's the ratio between the heat rate and the efficiency, and you'd see it's like 3,412 over eta. Why? Because you don't want BTU over BTU, you want BTU over kilowatt hour. Right? Just like in the units is a big deal for practice, because professional engineers like to use their own units. They don't want to, like everything is already, it's hard to change. Like when it, like in the homework today, homework 4, problem number 2, when he said calculate the power, he said it in tons, right? I mean, you could say, what in the hell? Why can't I just use kilowatt? Because like when you talk to actual engineer running a big central HVAC plant for a big building, they always tell you, well, this machine is like 70 ton and this smaller chiller is 40 ton. So we need to be able to be comfortable with those units too, okay? So anyway, all I'm trying to say is that first part of the course is all thermo, and it relies very heavily on thermo 1. And if you are weak on calculating the enthalpy or plotting things, TS diagram, you need to practice, because it kind of like really break my heart when I see people in the final don't know how to plot things, because that was really my favorite part as a mechanical engineer. I loved plotting things on a TS diagram, especially for a big cycle with so many lines. It just made me feel as if I'm really designing the cycle, just plotting it, you know, like you can really, it's like the blueprint. It's like the movie for the Avatar, I guess, or what, like the guy when like you kept saying, give me the blueprint, give me the blueprint. What was his name? Anyway, it's like really cool, something cool about plotting the TS diagram. Okay, and so today quiz will be about this, and hopefully you guys will do well and you'll be ready for the midterm. The reason why I also posted this exam is that the timing is important. People think that I know the material, but then they get surprised how slow they are when they solve the problems, because you never were in the mood where you work against the clock. So that's why the way to practice those exams, that's why I didn't post their solution. I don't just want you to read them. That would be just reading any example in the Selma book, but it's basically putting yourself in a closed room for 1 hour and check, did I really manage to write everything till the end to get within 1 hour, or that was just like too short for me and I need to speed up. Okay, so practice the time and make sure you always write what's given and what's required, because that is 30%. Just saying what's given and what's required. Yes.
So we just, on the exam, we don't need to like restate the problem statement, we just write given and required.
That is exactly right. So the question is, so in the exam, do we need to restate the whole problem statement, or we just say what's right, we just write what's given, what's required? Actually, writing the whole problem statement is wrong. You shouldn't write my words again. What I need to see is rho 1 equal, P1 equal T1, that's what's given. Required W dot and Q dot R. That's it, right? It's like basically reducing things to symbols, right? Maybe with a sketch, with the problem, you have a sketch, you plot your own sketch. So then when you say P1 and T1 equal this, then you know what's P1 and T1. Because the problem statement could probably be saying the inlet temperature to the turbine is this much and the inlet pressure was this much. The condenser expand to the condenser working at that pressure. Well, you don't want to write B condenser, you want to write B4 is 0.07 pound. So to be able to tell what is B4, you need to have this small sketch with numbers written in it, right? And I'm telling you, as someone who always gets nervous before exams, that especially before final, I used to vomit. Every single final, I would vomit, and that told me I'm in good shape. Like if I vomit, then that means that I'm in my game. I have my game right. So I always get super nervous, but when I like write this part and start by saying what's given and start writing P1 equal and T1 equal and with the unit, my brain calm down, because I already see things that I'm familiar with. Those are the condition. I remember this problem. I know how to do this. So it kind of eased me into the solution, right? And besides, we also said how the unit conversion, people lose a lot of points. Engineers lose things on other planet, Mars rover, because of units, right? NASA and Lockheed Martin had like different interpretation of the thrust. People thought this was in pound force. Those people thought in kilonewton, and that screwed up the landing. So that section is for you to make sure the units are all kosher. Everything is an SI. He tell you 70 bar, no, you write 7 10 to power 5 Pascal. He tell you the temperature is 20 degrees, you would say 20 plus 276. I'm not saying add, but just write it like 20 plus 273. This way, if the problem saying calculate the delta T something, you don't do the conversion. But in you are taking a mental note that it's 20 degrees C, therefore it's 20 plus 273. In case I'm going to use P equal rho RT, I'm going to use the Kelvin. But if I'm going to use Q is U A delta T from heat transfer, I'm just going to use the difference, right?
To clarify on that, will we only lose points on the exam if the final answer is not an SI? Will we lose points if we don't write everything?
All right, so the question is if the final answer is correct, but just like different units, does this allow us to, does this make us lose units, lose points or not? So to clarify, the exam will be graded, assuming that it's all like normal problem, you know? By normal problem, I mean you're calculating stuff, not sketching things, you know, all those weird things when he asks you to calculate, to plot, and I cannot. Why? So the answer is, assuming the problem is a normal problem, then 30% is devoted for the final answer. 30% is just for you to say, you know, given P1 equal 50 bar and T1 equal, you know, 500 degrees C, and required is eta and the heat rate, right? So that's 30%. 40% is for putting the right equation. So that's 30% for the final answer. One, if there is no final answer. Two, if the final answer is totally wrong. Okay. Four, if the final answer is correct with the right unit. Okay. And three, if the final answer is wrong or slightly wrong, not totally wrong, or the units is wrong, or the unit does not exist. So anything that affect the actual value or the units will take you from 4 to 3. Okay. I used to have a teacher that whenever we don't write the unit, like, I mean, we will get the number right, but we just forget to write the units. Calculate the temperature, 500, but we didn't say 500 degrees C. I mean, we didn't have degree Fahrenheit. We just used degree C. But he will basically say, no, that answer is wrong. Why? Because you didn't have the unit. The unit is part of the answer. Good? All right. So don't get nervous over the exam, but just prepare for it. And you know, over the years, I just always find out that people who let the first exam slip because they didn't prepare for it, it's very hard for them to get an A. I mean, it's really the first exam that put people down. So that's why you need to give yourself a winning chance, basically. That's what I always say. By doing well in the first exam, and then you can screw in the middle, the final or somewhere else. But at least in the first exam, you know, give yourself a winning chance.
Was it only the final exam that was set for 2 hours?
Only the final exam was for 2 hours, but all the midterm were for 1 hour. Yes, question here.
So we're going to do lecture before the exam.
We're going to do a lecture before the exam because my experience is that after the exam, people get so depressed and they leave. Or they get so happy and they celebrate. Either way, I lecture an empty class after the exam. That happened all over the year. Of course, the other bad side of the story is that if you lecture before the exam, no one is watching you and everyone is like reviewing the homework problem. So, I mean, I lose either way. So I think having it in the second term allow people who come late, you know, to catch up. At least that's what we get from this. You know, give them a chance to be late and still make it. All right. So we wanna go through the HVAC application of psychrometric chart, and then we will do the project and the homeworks, and maybe review a little bit if we have time for the midterm. Okay. So what did we study in the vapor compression? Is that the cycle will look something like this, and it take heat from the low temperature to the high temperature. This is the pH diagram, of course, right? pH diagram. And depending on, are you refrigeration and you care about this, this is H4 minus H1. Sorry, H1 minus H4, that's the refrigeration part. Or you are a heat pump and you care about H2 minus H3. That become the Q dot H. So that could be your output, or that could be your output, and in between that is the work. Work compressor is M dot H2 minus H1. Okay, make sense? Very good. And those problems, you solve them by basically getting the H's, right? H1, H2S, and H3, and then H3 is equal H4 because it's throttling, right? And real cycle will have a little bit slight variation. You could have a little bit superheat. And why do you get superheated? Because you are sucking heat from this guy. Right? This is the line where you're sucking heat from. This is the freezer in your fridge, the meat and the chicken and burger. Everything is sitting over here, and you go under them. You go lower than them so that you are taking heat from them. Right? You're getting joule for them so that they can stay cool. Because the fridge basically leak heat into them, right? So you take heat from them, and so they are hotter than you, yes, because you are cooling them. And so after you finish and you are saturated vapor, chances are you can get a little bit superheated before you go to the compressor. And that's good for the compressor. The compressor does not like water to go into the compressor, right? And that's not a great idea to have liquid into the compressor. And then this is isentropic, and this is the real one. And the same superheating that happened over here, that's the subcooling part, right? I mean, you could finish idly here, that's the ideal cycle, but because you are being cooled by this, the outside air, right? Then you can get a little bit subcooled. You see this temperature? This is the TS diagram of this pH. So in the pH diagram, there's just two pressure. One pressure, high pressure, low pressure. On the TS diagram, you can see, yes, there's also two pressure, right? But the pressure show up like this. See that is the pressure line. Again, people who don't remember the thermo one, that is the pressure line. So in this place, the pressure and temperature sitting onto each other. That is B saturation and T saturation, right? B saturation and T saturation are sitting on that line together. But in the superheated region, this is the same pressure like the condenser. This is the pressure that the compressor can see, and the compressor works from that low pressure to that high pressure. But what about this temperature here? Look at this temperature. It's way hotter than this. It's actually way hotter than this point. What do we call this point? The critical point. Like it's this guy, right? The critical point is here. So in the pH diagram, the temperature curve actually are those. See, those are the temperature curve. So when the critical point is 160 degrees Fahrenheit for that refrigerant, which is R4110, it go like this, and then go like this. That is the constant temperature. Yes. So that's not my solution. He's saying this is a cycle that is getting What can reduce? This is actually a great question for a free quiz. Your name is Michael? Charlie. Charlie saying, how is it possible that you are, I mean, look at those lines are isentropic. This is constant S. This is S constant. So if you are isentropic, you would move at that line. This line is actually going not constant S, not extra S when it's adiabatic, right? Remember? When it's isentropic, we go up. When we are not isentropic, real life thing, we go to the right. Because the second law say always extra entropy. Irreversibility friction, extra entropy. So Charlie question, but Charlie does not qualify for the free quiz because he cannot ask the question and answer it, right? So for everyone else except for Charlie, how is that possible? The line is moving to the left. I mean, isn't the best case scenario is isentropic? Could that actually happen? And why? Raise your voice, I can't hear. Raise your voice, I can't hear. You have extra heat at that point? So why it's shifting to the left? No, that's not the answer. How? How? How is it heat loss? So you guys are on the right track, but you didn't answer specifically to get your free quiz. So what's your name? Michael, he has a point that he probably think we know friction increases the entropy, and we know that the only thing that can decrease entropy is heat rejection. You need to cool it to reduce the entropy. There is nothing else. You do bad stuff, friction, mixing, all those bad stuff, you increase the entropy. You do cooling and you reduce the entropy. And this compressor is probably sealed inside, hermetic compressor, sealed in a refrigerant. And so that compressor is being cooled by the refrigerant around him. So not only he's not only adiabatic, but he could lose some heat to the refrigerant that is around him. Yes. Will that come from the one? Yeah, the one could be swimming around him. Like if we Google. Let me show you first this, and then I can try to answer your question. So hermetic compressor. So in those hermetic compressors, everything is inside one big package, and all you connect is refrigerant in, refrigerant out, and electricity. But everything else is sealed. You just give him the refrigerant, and you get the refrigerant, and you connect the cable. Okay, so what is the question? Say that again slowly. 1, 2, 3. 180-degree return. Where is the 180 degree? There's no 180 degree. This?
He's talking about like the pipes changing direction.
If the pipe turning direction, that make the temperature get cooler? Well, yeah, but it's not like really sharp corner, no, they wouldn't do that. So this is not the actual pipe, right? This is just the sketch in this diagram. I bet the pipe itself is gonna have a really nice turn. They're not gonna, like, why would they create their own pressure drop in a pipe? They are not gonna have really sharp corner in their side.
He's talking about in the heat exchanger, like the internal tubes go all the way down.
Right. Again, that even inside the heat exchanger, they will try to make it smooth turn. They're not gonna jeopardize. They're not gonna risk the pressure drop just because of the geometry. Right? There's no point. All right. So that's what we basically figure out we can do in a vapor compression cycle. So this, the fact that we can move heat from low to high, that is a blessing for HVAC application. So now let's see what they can do with that HVAC application, because sometimes we want to cool things, sometimes we want to heat things. So we have seen this before. We said that different building will have maybe different zones that allow them to cool different places to different temperature, right? And in every place there is like an inlet duct or like a supply duct that bring the cold air, and then a return duct that they bring back the air and send it to the air handling unit or AHU. So the AHU take the bad air, and it could be bad because it's too hot or too cold, depending summer or winter, and basically fix it for you. Okay, and they fix it for you by, that is the workhorse. That's what's setting to either take the air up if it's too cold or take the air down if it is too hot. Okay, and the unit thing, again, HVAC is very professionally dominated by by the industry. So we basically have to do the calculation according to them, not according to the equations. So the ton of cooling is what? 12,000 BTU per hour. And so 1 watt is 3,414 BTU per hour. That's why the kilowatt hour to BTU hour becomes 3,412. Okay, that's the reason. And so then you can figure out what is 1 ton in kilowatt. How much is it? Was it like 3.5 something? How much is 1 ton in kilowatt? You have to divide this over this, 12,000 over 3,414. How much is that? 12 over 3.4 is, anyone? 3.51. So that's what is 1 ton in kilowatt. So rather than saying this machine is 80 ton, they could have said this machine is 80 ton times 3.5 kilowatt. But no, they rather use ton. Okay. It's confusing also because you would think ton is weight, not really power, but ton of cooling is power. All right. So now all those air handling units, they need the cooling coil of a mechanical vapor compression to come to them. That cold water, they need that cold water or cold refrigerant or whatever your working medium is. They need this to come to them in the air handling unit so that the air can go and get cooled, right? So all that chilled water get cooled by a chiller. And that chiller is simply the mechanical vapor compression cycle. So that chiller could sit on the roof, or it could sit on the basement with a place to cool his own condenser. Okay, so the chiller is simply a mechanical vapor compression cycle. Okay, and so here is the air-cooled chiller, and we have a lot of companies in Tulsa that actually make those big heat exchanger for the chiller. They make them so big, and they ship them overseas, all over the world too. And they make them so big that it has to be basically lifted by cranes. That's how big it is. And so what is that? That's just a mechanical vapor compression. The evaporator, the compressor, the heat exchanger or the condenser, and the expansion valve that take you from 3 to 4, drop you down to the low pressure. And you can see how the evaporator is such that it look like what to you? Like a counterflow. You know, remember heat transfer, counterflow, and barrel flow. In counterflow, things go like this. The hot fluid is going this way, the cold fluid is going that way. The reason why they do this is that it allows you to take the hot guy all the way down to really much better temperature, much lower temperature, right? So if I have counterflow, let me plot this is just the distance across my heat exchanger. Okay, so in a counterflow, the cold can go like this, while the hot can go like this, while the cold go up like this. Okay, so you can see how the exit temperature of the cold is actually could be higher than the exit temperature of the hot. That is pretty useful, right? You wouldn't be able to do this if you had barrel configuration. So in a barrel configuration, both go from the same direction. The cold and the hot, they enter from here and go like this, and the hot will go like this. So the dream, is just to meet them kind of in the middle. So you are preventing yourself from achieving the dream. What is the dream? The dream, and we'll talk about this next week. The dream of every heat exchanger is to take THN and do what with that? Take it all the way to TCN. I mean, that is the dream, right? You have like 80-degree oil, hot oil, and you want to cool it down all the way to the air temperature that you are cooling with. Okay, so that would be the dream, to actually go like this. Okay, the dream could also be the opposite. The dream could be to take the cold guy, right, and take him all the way up to this, to take 2CN and heat it all the way up to 3HN. The guy that will be able to achieve that dream is the one that have the resources for it. And it will be the one, if you remember, the one with M.CP minimum. If you compare M.CP of the hot and the cold, the one who has the smallest M.CP, this is the one that is moving slowly, he's taking his time in the heat exchanger. He's moving with a very M dot, very small M dot, or the smaller M dot and the smaller CP. So it's not very expensive to heat him. The CP is how many joule it takes to jack your temperature up 1 degree. So if your M dot CP is smaller, if you are the guy with the smallest M dot CP between those two guys, then you can the one that will achieve the dream. That dream is called delta T max. That's the delta T max available in the heat exchanger. The difference between the lowest and the highest, right? So a counterflow has a chance to do that. There is a potential, but barrel flow, there's no way in a barrel flow, right? You had a question. Okay, that's what I do with my kids too. I just like stole them. Okay, I'll try to ask you quicker next time. So you can see how they are trying to divide the flow so that you are trying to do this counter flow rather than just like let's send them and let them mix together, right? When you are forcing him like this, the other guy, so there's one in the pipe, right? There's flow in the pipe, and then there's flow that is, they will probably let the flow in like this, and then it will move in a counterflow configuration, right? So this is for like big building, right? In small building or residential building, that same cycle or that same mechanical vapor compression exists, but with different configuration. You will have the outdoor unit sitting on the backyard, and then you will see pipes going into the house. And one of them should be insulated, and the other one should be not insulated. Which one should be insulated? The inlet or the exit of the
one going into the house.
yes, because that's the one ready to do the job. And the one that is going outside, that's the one that basically should get cooled, right? So you will see the pipes in, and then those pipes go to the indoor coil. That indoor coil, depending on summer or winter, this indoor coil could be the evaporator or the condenser, right? Could be the hot or the cold, right? And this is just you're bringing the return duct from the house, and then maybe a filter and blower, and then the cooling coil. And then you will have extra heating, whether it's electric or in many cases, it's just like a furnace powered by natural gas, that if the COP of that heat pump is not high enough in the winter, and why it wouldn't be so high in the winter? Why does the COP of the heat pump will suffer in the winter? Yes, it's too cold outside. So on a pH diagram, what's going on is you went too low, right? So this part, compared to this, is basically just too much. It takes a lot of work to go from here to here. Okay, and so the COP, if it gets really, really cold outside, the COP in the winter could drop to how much? Theoretically speaking, it's really, really cold. The COP, that would be an excellent question for multiple choice. In case I want to have multiple choice. What is minimum COP in the winter? Let's move to Alaska. We are in the University of Alaska, right? And it's very cold in the winter. I'm telling you, what do you think the COP of our heat pump right now? Huh? How much? What is the minimum COP that you can hit in the winter? Minimum COP, give me a number. 1, excellent. And that will happen when the Q dot L would be almost 0, right? Q dot L will be almost 0. And then the COP is what for a heat pump in the winter? Q dot H over work compressor, right? It's this over this. And as we go lower and lower, this part become almost nothing. Remember, Q dot H is actually Q dot L plus work compressor. Why? First law of thermodynamics saying Q dot L plus work, leave as Q dot H. Make sense? You are sucking Q dot L from the evaporator, adding work, and everything leave at Q dot H. Yes. But if you are trying to cover the unit to make it warmer, but the outside unit is trying to get heat from the outside. It's trying to suck heat from the outside. Yeah, if you want to preheat the air around it, but then, I mean, what is the point then? Right? So the point is, if you realize that the COP is gonna really be sucking like this, right? Because it gets really cold, he will turn on the external unit. They call it the auxiliary unit. The auxiliary unit basically fire the natural gas and you get the heating in the duct by the natural gas. Because notice that this heat pump running by electricity, and that electricity already are running, or this electricity was generated with 40% efficiency from the natural gas burning in Jenks power plant across the river. So you already lost 50%, more or less, 50% of the natural gas in the power plant to get that electricity, right? So you can just fire that natural gas in your furnace and you get 100% of it in the heating, right? So to make sense to use that from the planet point of view, not from your house bill point of view, from the planet point of view, assuming 50% efficiency of Jenks power plant, this heat pump should be used for heating in the winter if the COP is how much or higher? 50% power plant. That's an excellent question for the example. Especially if I make it like 60%, like Owasso, like say we live in Owasso, the power plant efficiency over there is 65%. But let's make it 50% so it's easier in our mind calculating. 50% efficiency. Jenks power plant, natural gas burn, electricity 50%. Then you as an engineer feel justified to turn on your heat pump for heating if its COP is how much? 2 or higher. If it's less than 2 or higher, I could just like burn the natural gas myself, right? Make sense? Right? And you can actually see, like in my house in the control, you can actually force the auxiliary unit to run. You can say auxiliary unit, run it. You don't have to make the COP, you don't have to make the heat pump run by electricity, right? You can override and say, I want auxiliary heat right now. Yes.
How do more modern heat splits, heat pump systems that are standalone, how do they overcome that?
I don't understand the question. Are you saying like how? Because are you asking me? Is their COP is always higher in the winter? I don't know whether that's true or not. Why do you think their COP is higher than 2 in the winter?
Why do I think?
Yeah.
Well, if somebody's relying on that as the primary source of heating.
I mean, it's also for convenience. I have been in commercial building where they have like different tower in their building, and one tower is running on a heat pump, right? And the other unit is completely in different building just because the building was done recently and they don't have the room to run the plumbing. And rather than having actual furnaces and boiler to heat the house, to heat the building, that new building is all run by electricity, heating by electricity, and it doesn't make sense. And they know, but there's no way I'm gonna run or make a boiler for them over there. So big building have big boilers for one wing, and the new building is all split units, and it sucks, but it's very convenient. But also think about, when there are like small spaces compared to a big bank or a big stadium, or sometime if you are running small spaces, it makes sense to have small units, because the saving is not that each unit is working efficiently. The saving coming from the fact that only one unit will work. There's only one tenant and he's running his stuff, but you don't have to heat the whole building, right? So that could be the saving by splitting things. Very good. So notice how he called this air. This is, by the way, you will not find this in the book. This is from Ashri. Ashri had excellent, if you become a student member of Ashri, I think it's very little, but you get access to all their textbook. So Ashri is one society, unlike AIAA and SME, that really make a lot of good educational resources for their member, So this is from their book, Fundamentals of HVAC, I think. And so they call this air-to-air heat pump. Why air-to-air heat pump? Because the heat pump is moving energy from the air to the air, from the outside air to the duct air inside your house. Air-to-air, okay? So air source, that's another word for saying it. They call it air source heat pump, meaning the unit, outside unit is sucking heat from air. Okay, and that usually requires a lot of surface area because if you remember from your heat transfer course, H, heat transfer by convection from air, is high or low compared to a heat transfer by convection from water. Air has smaller or higher heat transfer coefficient? Lower, way lower. And that's why they compensate this by what is the one equation heat transfer that everyone should remember? Q dot is U A delta T. If there is one course you should remember from your heat transfer course, it's this. This equation tells you if U is small, you better make A big. And because the heat transfer coefficient, when it comes to air, is small, then the surface area of the air heat exchanger should really, really be big. And that's why they always, how do they increase the A for heat transfer on air surfaces? How? Fins, right? Like, I mean, if you look at any motorbike and you look at the engine, you will always find, you know, like tons of fins sitting on it, right? Maybe a motorbike engine, right? Why so many? Because they know if I want to cool, H is not helping, I need to have a lot of area. That's why they make all those fins. So you will never find fins on water, like things that are cooled by water, you will not find fins on them because the H is big enough, right? Way big. So if there's a pipe with fins on the outside, you know that it's air cooled from the outside. But if that pipe is like no fins, you know that it's water and water, or refrigerant and water. All right. So that unit, if it's getting heat from the air, then it's called air source heat pump. But if you are, the refrigerant is on one side and the other side is water, that would be water source heat pump. Okay, so it gets cooled by the water. So in a big building like this, those units could be water source heat pump. So you just send the water to them and they actually use that water to get the heat into the air or out of the air. So become heat source, water source heat pump. Okay. Oh, and next door, you know, across the river, they make those water source heat pump a lot. They make them like crazy. That's like maybe one of their best products. They are very compact, right? And you can put them in any place in the building, and all they take is just like a water pipe going to them, and a water pipe coming from them. And electric power, of course. Electric core, water and water. Water in, water out. And that chilled water going to the unit and coming from the unit, that's basically their outside universe. The water pipe coming and the water pipe leaving. And then the small compressor inside use that water coming in and out to basically heat the air or cool the air. Okay. Now the next one is ground source. So air source heat pump, water source heat pump, and then ground source heat pump. And that's when you don't exchange with the air or the water, but exchange with the ground, right? And so you can see here how here is the mechanical vapor compression or geothermal water to water heat pump. So water on this side that go into inside the house, maybe inside the cooling unit of the air handling unit, or maybe into radiating unit for heating. That's actually pretty, I mean, both pretty classic and also pretty modern. So pretty classic. When I was a student in Michigan, maybe 20 years ago, I used to live in the university housing. And so we had central heating, like, you know, hundreds of houses, family housing. If all the families, like students with wives and stuff, and children, and they were all living in those family housing. And there is one big central plant that heats and then send water, hot water or hot whatever, into the pipes, and these pipes come to those small units sitting on the, like we had maybe 3 units or 4, one in the living room, one in the bedroom. It was 1 bedroom apartment, 1 living room, 1 in the bedroom, and 1 in the restroom. And so those units get, you don't turn them on and off. You just wait when the university side, now it's cold enough, let's turn on the heating, and they kick on the heating. And then those radiating unit just become hot, and you heat your house. And the funny thing was, my wife had like a lot of, like, because they were like under the window, she had a lot of plants on them. And we come one day and like the plants are dead because, not dead, but they just like collapsed because the heating from this was so big, you know, all the plants basically just died. But it's also, so it's very classic, because that was very old system. And actually, if you go to main hall where the library is, and you look at how the corridors are heated on the 2nd floor, you will see those radiating units across especially in the internal part. If you go in the corridors inside the 2nd floor, you will see all the walls are heated by this. But it's also a new thing, because what's nice about it, it is for cooling and heating. What do you think? Noise. There's no noise. You're just like sitting there to feel like luxury, you know, like the place is cold and you don't see you don't hear the HVAC like shh, and right? So it's pretty fancy. Like really expensive buildings in Tulsa, commercial one, they also have this for cooling. Okay. Yeah. Yeah, and very you know, like the condos and stuff, they would have this. Right. And then on the other side, rather than cooling the outside air or heating the outside air, which might not be that hot or cold, summer, winter, you actually send it to the ground. And when you bury it in the ground is usually much better than the air. The air in the summer would be like 80, but the ground is 75. That's nice, right? Winter, the outside, it is freezing, but inside it's pretty good. And that's why the pipe survives in the winter, right? Hopefully, right? We'll see what will happen this year. But the pipe survive because it's deep inside and take a lot of time for the ground to really get cold. And so your fluid will be exchanging heat with that really cold, that really convenient environment. Let's call it like this. So the COP will improve if you have a ground source heat pump, right? Why does the COP improve? Because your cycle, your pH diagram here, rather than having to work with this, he will work with something a little bit more favorable. Ouch. He will work with something more favorable in the summer, right? So that drop allow you to say, I don't have to go that high. You can just go here. That's good enough for the compressor to work. And so the compressor does not have to work that hard because he does not have to go that high. Because the outside, which is the ground now for him, is a little bit cooler. Right? So that reduction in the delta T allow you to. That's why also, you know, one important thing that we all know is that when it gets really hot in the summer, you need to be nice to your heat pump and do what? Take the house here. Say rather than 70 guys, it's really hot and outside, it's 100 degrees outside. Maybe we should be happy with 80. inside the house, right? So if you take the house up, so now the house is sitting here, then the compressor is not working as hard, right? So basically what I'm saying is like tie the inside environment with the outside environment. When it gets hot, maybe you need to take the house hotter. When it gets very cold, you need to take the house down too. But it does help if you have the ground. Of course, this costs a lot of money, right? But people from when they start, they can do that, especially when it's a new project. So they build this new Catholic cathedral, almost like really big church in Stillwater, like maybe like a few years ago, 5 years ago. And they made the whole HVAC system relying on ground source heat pump. They built the wells and they basically did the calculation and they figured that this would save them a lot of money over the lifespan of the church, right? Although it takes money to make the well, but for a project that's supposed to live forever, you know, it really pays off. All right. So now we'll talk about what is the setting of the air that the air handling unit should do. So the air handling unit is getting the return air from the room, and that usually is not that bad. The air coming back from the room, it's a little bit hotter, but not as hot as the outside air. When you get the outside air, it's usually really hot, and it takes a lot of energy to cool it compared to the return air. So if it's up to you, you would say, let me just keep running forever on the return air. But of course, the air will smell bad and people will complain. And so you need to bring some outside air. And sometimes you don't even have a choice. Sometimes that outside air comes despite your design. How? Where it will come from? Huh? Yes, infiltration. And there is a way to calculate that infiltration, right? We'll see how. So that infiltration always happens. And that's why when BSO send you a bill and say, well, this is an efficient house, here is your house, right? If you are not an efficient house, you know that your windows are leaking, the doors are not closed, people don't leave behind, like don't close the door behind. So ideally, you would like to be in this place, okay? So this is what psychometric chart, and he's saying, again, this is from Ashley. They say, well, summer and winter. So people will require different temperature between the summer and the winter. And it's really funny, you know, when like people in the summer would say, like, we want to cool it to 70 degrees. Your kids would say, we want the house to be 70 degrees. But then in the winter, when you said it on 70 degrees, you're like, no, it's too cold. How come? You were saying 70 was good enough for the summer. Like, no, we want to have 80, right? So there is, of course, seasonal adjusting. And there's also clothes adjusting, right, between the summer and the winter. And when people wear more clothes, they need more cooling. Makes sense? And so this is from Ashley. He's basically saying, well, here's how basically you design a new system. You have to figure out the load model. You start weather, right? Internal loads, how many machines, how many computer, and you figure out the load. And based on that load, you come up with the system model. And then, so that house, that plant, that classroom require this many BTU per hour. And then you pick the architecture. I'm going to have a chiller, or I'm going to have heat pumps, or I'm going to have a boiler. And then based on this, you basically do the economical model and figure out how much it will cost over the lifespan of the project. So the load part, you guys asked about how we can calculate the load. And also when you come with the system model, what is the design criteria? So again, Ashley had chapters and chapter for every single space that you can imagine of this, like basically doing HVAC for it. Classroom, commercial, residential, hospitals, clean room, like the clean room that we have here in the first floor. We have a very fancy clean room if you have ever been on that wing. So you can see here winter and summer, what is the indoor design condition, office, conference room. So this is office building. The cafeteria has its own temperature and its own humidity, right? And the kitchen, there's no humidity control for the kitchen because you'll go crazy because of all the vapor that come out. You cannot cool that. And here's hotel, for example, guest room, lobby. You can see the lobby can be a little bit colder than the guest room, and the relative humidity required. So what else beside the loads of the people? The infiltration, right? The infiltration and the loads. So there is heating load and cooling load, right? That's self-explanatory. And here are the people and how much they can put BTU per hour. Adult male, adjusted male-female ratio. And so a person seated at a theater, seated at theater at night, seated very light work, moderately active work, walking, secondary work. So for each one of those jobs, bowling alley, factory, gymnasium, look at the gymnasium, they can put 2,000 BTU per hour. So you add all those total heat and also the division between sensible and latent heat. So the sensible is just like dry heat that they send, and latent heat is simply their M dot HFG, M dot steam they are sending out time HFG, latent heat evaporation. Okay. So you add the people and you add the machine. For example, the lights. They tell you how the lights is simply watt per feet square of building. So if you know the area of the corridor or the area of the auditorium, you can basically say, well, that will require this much watt. Okay. Cooking appliance. And then the building envelope, that will leave this for architecture engineering, but that is a very complicated problem too, about like how good is the ceiling on the wall, whether they have this nice wall or like leaky wall, right? But in this course, we will just base it on the delta T. So like if I tell you, if I want you to calculate how much losses is coming from a space, I will give you the heat transfer coefficient. I'm going to simply give you this, right? And so you basically figure out what's the delta T and you multiply by the area of the wall. That will tell you how much Q dot is leaving. But we are not gonna. You in the heat transfer course, if you remember, when you have wall with multiple layer, you guys calculated the Q by conduction plus conduction plus conduction. When you have a bunch of series in parallel, that's how they do it. But you need to require. Now the infiltration, that's important part. So the infiltration is how much outside air come into your house, and you need to cool that outside air. Okay. And the method we're gonna use is called air change per hour, ACH. Okay. So we are trying to calculate how much Q dot for heating or for meeting the cooling load of house with leaky windows and floors. So if it's very tight, a good house will have 0.5 ACH. Leaky house 2. What is ACH? That is the volume. How much is the volume of the air inside the house? House have 20 feet cube. Then when you say it's 0.5 ACH, that means that 50% of that air will come to you every hour from outside. So if the house is like, I don't know, 20 feet cube, then, and we are assuming 50%, then 10 feet cubic feet will come every hour from the outside with their outside air temperature and their outside humidity. And you have to basically make sure that your machine can take that amount of air every hour and take it from those high temperature and high humidity down to the design condition. Okay?
Proportional to the volume inside the house.
It's the volume inside the house, and either you're gonna take point, those are the two numbers that we need to remember. 0.5 every hour or 2. Twice the volume every hour if you have a leaky place. If you're, you know, your children don't close the door tight, although. So all you need is the building volume. And here's an example. Volume 30 feet by 60 feet. That's the house. And the height is 10. So the volume would be 30 times 60 times 10. And here's outside air. It's so cold. Okay, 0 degree Fahrenheit, probably North Dakota or something. And at such very small, where is that? Very small temperature on the TS diagram, sorry, on the psychrometric chart. Where would I be at 0 degree Fahrenheit? To the left, right? I'm probably going to be here. And you see how the phi at 100% is collapsing on the floor, and this is like 0. What this is omega, right? So it's fair to assume, first of all, you are not going to find the 0 degree. You're not going to find it on the regular psychrometric chart, right? So you will not be able to basically figure out what's W. So it's fair to assume that when you are that cold, it's going to be 0 humidity, right? Make sense? Because we are like squished between the 100% that come on the floor and the x-axis. So this is a common assumption. Just assume it's 0. Okay, specific volume, and he say it's 0.5, so that's a very good tight house. And the indoor is this, with a desired unit of this. What is the infiltration load? The infiltration load at this time would be heating or cooling. Would be heating load. You're gonna take, like, very cold air will come in, and you're supposed to heat him up to 68, right? So he's calculating the volume, first the total volume, then only 0.5 of it, and then he is adding per hour because it's air change per hour. Okay, that's important to remember. So we assume this is happening per hour. Okay, and so because he had the specific volume, then he can find the mass, and then he would say that the sensible load is CBT. So one problem also with that part, it does not exist on the chart. How can I get my H? How do I usually get my H on the psychrometric chart? It's important for the midterm. How do I get the H? I read those lines, right? Those are the H. They have a scale over here, right? What's the unit for the H? Kilojoule, kilogram. Kilogram what? Dry air, right? So it will be, you will not be able to find the 0. It will be just like too cold, right? So then what we're gonna do then? We will just assume that CB delta T, that's the sensible part. Remember, the sensible part is the horizontal or the vertical? Sensible load is the horizontal, and this is the latent, right? So he's saying that if you want to get the sensible part, you can just assume Cp delta T. Temperature, Cb. Okay. So you say you can look in vain for 0, but you will not find it. So just use delta H Cb delta T. And so here is the Cb delta T from 0 to 68. That's how much. Okay. And for the delta H latent, the latent load, that's the vertical up. You want to increase the humidity. If you send 0 degree, not 0. If the air is so dry and you send it on the people, their eye will be itchy and their skin will be, and their lips will be, it will start to crack and stuff, right? Everything will be irritating. So a good air conditioning system will add water to that very, very dry air. And so how much do we need to go up? This HFG. What is this? We started with 0, and this is coming from the desired condition. Okay, what is the desired condition? You say you want to be here. You want it to be at 68%, right? And whatever humidity. What was his? Did he say 40% or 60? What was it? 50? Okay. So whatever that point is, then you want your W to go up to this, right? So you're going to go up from here to here. So 68 and 50%, you get that number and you assume it's 0, right? And you multiply by HFG. And of course, HFV is function of temperature, but you just have to get a good average between those two temperatures and just get what is HFG in this range. That will become the latent heat. Okay, so Q dot length is m dot delta H and Q dot sensible is m dot delta H. You get BTU per hour and you get BTU per hour. That sounds like a good problem for the midterm. Just calculating the infiltration load. Okay, and what would be cool is like like we say, compare it when it's like tight and leaky house and compare the difference. So it's basically 0.5 and 2, right? You actually don't even have to do the calculation of all the question was calculate the increase. It will be just like 2 over 0.5. It will just be 4 times, right? Okay, cooling, well, the air is actually hot outside. So 99 degree and the wet bulb temperature is 75. So he can give you the outside condition by temperature and phi, or he can give you instead on this chart, he can give you what? He can give you the dry bulb temperature and the wet bulb. How do I get the wet bulb? Those guys, right? So this would be T wet bulb, right? So he said it's like 75 here, and this was 99. And so you meet here. Like where the 75 came from, 75 would be this. And it actually will match 75 here. So that would be the wet bulb. That was the quiz last week, right? And I uploaded the solution, by the way. Did you see the solution for the quiz? No? So yeah, because you guys complained that you wanted the solution to be always printed. So I did this. Let me share my screen. Actually, Right, so over here you see quiz 5 solution. So I click here. And and you can see how so last week he was saying, for this condition, find the wet bulb and the dew point. So the wet bulb is this way, you read this number, and this is the dew point, and you read this point, right? And there is actually a program to a MATLAB program that calculate this, both of them. Just is taking time to. Weird. Should work. And I also uploaded the solution for the homework, homework 3, and I'm gonna upload the solution for homework 4 today. So homework 3 solution is already there. See 3B1 and 3B2 and 3B3. Okay, you can find the solution. So you find the chart and the equations and the label, everything. Good. So the wet bulb is basically those lines, right? So you start for 75, you come here, and then you intersect with 90. What that means is that, like, if you are here, if you're 100%, if you are here, or if you are anywhere in that point, your dry bulb and wet bulb are the same. That's what it means. If you're 100% humid, you don't have wet and dry, you just have one temperature. The fact that your wet is lower than your dry is because you are like here. So you're like 100 degree, but your wet is 75. That also, so that's lower humidity. That also, that difference between your dry and wet, that's how effective evaporative cooling could be. Like, we can cool you all the way to 75 if we just spray water in you. Yes, we will take you to 100%, but your temperature will drop. Okay. So infiltration cooling, here's the dry and the wet. So you find out where you are in the cyclometric chart. And here is the design condition, and he wants you to figure out what would be the cooling load, right? So, but he's giving us the M dot. So if this is the outside and this is the inside, and we are cooling, right? So this would be the latent load, and this would be the sensible load. Make sense? Sensible load. So if I establish this point, because he said it's 99 and 75, okay? And for the inside room, he said this and this, or like maybe he said this and the humidity ratio. Once you establish those 2 points, you can read the H here. This is the H. You see that? The H. And you can read this H. And then vertically and horizontally, you intersect here, and that would be the H. So 38 minus 31, that is 38 minus 31. How much is that? That is the latent heat. And the 31 minus the 24, that is the sensible heat. Okay, so if you want to cool that outside air back to this, you have to pay for this and this. This many BTU per kilogram dry air and this BTU per kilogram dry air. Now, if you figure out what is the M dot, how did you get the M dot? Volume of the house multiplied by how many air change per hour? Is it 2.5? And you divide over the specific volume, right? And specific volume, you can get it also from the cyclometric chart, from those vertical lines. You see the volume, cubic feet per. So if it's here, that air would be the one that will leak in. right? So you'll be able to calculate the step volume. So all those guys will allow you to calculate the M dot. Multiply delta H, you get yourself the. Good. 6 o'clock. Let's take a 15 minutes break and we'll meet at 6:15.
How long? How long?
15 minutes.
calculate the correct COP. By the way, my way about this, I lowered the efficiency of my compressor. and my COP. I'm not efficient. But I can't lower the efficiency of the pump. Oh. Worst case scenario. All right. You finally get it. Oh, man. You've been 4.0 for 120 hours. And you finally got it. Oh, man. Which is 142. It's worst case scenario. I sat and stared at it, asked the TA. Looks great. I know it looks good, but it's obviously not. That's got to do that.
All right, 6:15. 6:16 actually. Right, let's start again. So, what did we learn in the first part? Loads have tables, and there are methods to calculate things like infiltration load, okay, like this air changing thing. And so once you figure at the end of the day how much is the BTU per hour that you need to move, and what is the design condition, the indoor design condition, you can figure out basically where you should start and how it will end and how it will cost, right? So that's where this chart, those scale, some of them come with protectors, some of them just come with this, you know, the design point here, not design point, but the way to read that scale. And we talked about this last time. So let's stress this again. So this is QS over Q total. Q sensible over Q total. So if you are standing here at that thing and you put a line like this and it go to 0.75, that means your sensible load is 75% of the total. Okay. All right. So now this point here, assume this is your design condition. He said, I want the indoor to basically be sitting here, 50% and 70 degrees Fahrenheit. Okay, he wants his house to be 70 degrees Fahrenheit, 50% humidity. And this line coming from QS equal 70%, 75% Q total is coming from not just infiltration, but all the load that you calculated. You added the TV they wanted to do and how many people there. At the end of the day, this is how much their QS, this is how much their QL. Therefore, the ratio between the QS and the total in that place is 0.75. Okay. So because it is 0.75 on that scale, then if you put air in the room, the air will follow that line. Okay. So if you want to end up here, because that's the design condition, you need to supply air for them along that line. What is that line? This one is parallel to this guy. Why did I use this guy? Because that's where this point is. This is where I can use that chart. You understand? So sitting at that point, you can get the ratio, and then if you declare this is my design point, then make parallel line to it, and that's where you should supply the air. It should be here, here, or here. You send air at that place, and it will follow that line until you get it here, and that's where you extract that air, send it back again into the machine. Make sense? Yes? No? What's confusing? The air that delivered air, the delivery air need to be along any point along this. How far it is, depending on the m dot. So the load that we are pulling, the Q dot L total, not Q dot L, Q dot total, is going to be m dot time delta H between this H and this H, if we're going to deliver air here. If we're going to deliver the air here, then you have bigger delta H. So simply, if you have more m dot, you can deliver the air a little bit, not that cold, because there is a lot of m dot that will pull m dot delta H. But if you have smaller m dot, because the ducts are small, because you don't want to have high velocity, then you'll have to have bigger delta H for the cold air that come in, so that he can pull all the Q dot L in his way. Okay. Yes. Very good. So now the wet cooling, the wet coil temperature, that's also very important to realize. So if you have this air here and you want to drop the humidity to that level, obviously you can take that air and cool it down up till here, up till the dew point, and nothing will happen, right? And then you can drop it, you can cool it all the way up till here. And once you drop it up till here, you have now the same, or you have the target humidity. But he's saying that you actually, if you have the cooling coil, you don't do this. I mean, you wish the air will go this way, but you actually have to take the cooling coil all the way down. The cooling coil, the one that's the refrigerant is cooling, you have to take him all the way down to this. This is the de-evaporator. It has to go all the way down here so that you would have air that is like this. So why? So he's saying that the air leaving the cooling coil will be at that point rather than at this point. Why is that? What is the question again? So the question is, here is a psychrometric chart, and we have air over here at ω1. And they said, we want to drop the humidity to ω2. Please cool it for us. Figure out what is the T evaporator. I'm going to cool this air by sending it into a cooling coil And that cooling coil is the evaporator of a vapor compression cycle that have a condenser and have this thingy, right? And so here's a compressor, here's TH, and here's TL. And so the question is, for now, what is this TL? So that I can design my, see, that would be perfect for the exam. I start with psychometric, then you calculate what is the TL, and then I move you to the vapor compression cycle. And I say now, if we wanna take the refrigerant from TH to TL, how much it will cost, right? Electricity. And then the third problem will be, well, now we're gonna generate this electricity with a Rankine cycle. How much natural gas does it take to actually do this? That would be perfect example. So the question is, what is the TL that the cooling coil need to send its refrigerant so that your air can drop from omega-1 to omega-2? What would be that air temperature? Sorry, what would be the TL? How can I get that? This is T air, T1. The T refrigerant would be, help, definitely not this one, right? Because if I cool the air till here, nothing will happen, right? Nothing humidity-wise will happen. I will have the same omega. So how cold should the air get to drop to omega-2? Maybe here, right? You would think here. You think this is TL. And you think that air will leave here because you are putting him in a cooling coil like this. He's saying that, no, you need to cool here. And the air will go like this. So the question that I asked is, why? Why do you have to go further? And actually, this brings a lot of good memory to me. So, and you will understand why if you answer this question first. The air actually leaving the cooling coil is basically here rather than here. I mean, the air leaving the cooling coil will not be 100% saturated. There is humidity is what? Huh? I can't hear. The air humidity, this is the moisture content, right? And this is the target moisture content. This is the entrance phi1, right? And this would be the exit. The question is, how could he leave here? So the memory is, I was taking my HVAC course when I was undergrad, and the professor was plotting. He was like a really very famous professor in HVAC industry. Like he did a lot of consultation with a lot of companies and a lot of construction companies specifically. And so he was basically saying, well, this is the exit temperature of the cooling coil. And I remember I raised my hand and I said, well, how could he leave here? Shouldn't it be saturated? I can't hear. So my question is why it's not leaving at the saturated line? Why is leaving here? That's what I asked him. And at that time he said that it was like a really, really good question. Huh? My question is why it is not 100% saturated? Huh? No, if you are sitting at that line, it's not water. It's just that you dropped all your water and you're 100% saturated. You're not water. You're just 100% saturated air. Huh? So yes. No, the whole thing is sitting at the same pressure. The whole chart is psychometric. Chart is all at atmospheric pressure. That water vapor dropping does not change the pressure, the total pressure that much. So what is the explanation? How did he explain it? That no, the cooling coil will not result in 100% saturated air. It will be less than 100%. How is that possible? I thought that we cool, and then once you get to that temperature, then he will start dropping his moisture content. And so the idea in my head is that at that time that you move along that line. So there is no way you wouldn't come out saturated. If you are going to a cooling coil, you should leave saturated. Your what? Who is getting heated? The coil is getting heated? No, but the coil, the refrigerant, let's look at the refrigerant. This is important for you to remember. Where is the refrigerant? He is on a TS diagram, huh? Or maybe pH diagram. Anyway, the refrigerant is actually doing this. Once he gets into the coil, he is doing this. The refrigerant is, you see that? That's TL. While the air is doing what on top of him? The air is doing this. The air is getting colder, colder, and colder, and colder. Why? Because the refrigerant is sitting at, I don't know, 10 degrees C. The refrigerant is saturated temperature. So, and the air is being cooled, cooled until he hit the T dew point, right? Which is this T dew point. And once he hit that point, then he starts losing moisture and he become 100% saturated. And he lose moisture because he's 100% saturated. And then you cool him more. Like you have to hit this 100% so that they're like, I cannot take this water anymore, man. It's too cold. And he start dropping his water. And he moved from here to here to here to here to here. That's the idea that I did understand, and that's the idea that I told you so far. Okay, but right now I'm telling you that actually he will end up here, not here. And the question is why? Yes. I can't hear. You have to sit up front or raise your voice. No, there is no insulation. No. That refrigerant is really sitting at that temperature. So what is the reason? Okay, so to save our time, it's because there is always, I mean, now think of yourself as an air molecule, okay? Imagine yourself an air molecule, and we are going through that coil. That coil everywhere is sitting at, I don't know, 10 degree, really, really cold temperature. And we as air molecule, we just go through it, and the people, the some of us that get near the coil, they were like, oh, so cold, and they drop their water, while the rest are doing what? Are just moving between the pipes. So what I'm saying is that at every moment, there is always a mix between this and between this. Along this line, there is a mixing between those who didn't get cooled and those who already are there, sitting in the coil and get really cold. And so you will slowly get this point, will get this point, this point, this point will get slowly closer until If you spend infinite time with that evaporator, you will end up here. But I didn't give you permission to talk. Wait. No, wait until I finish. Wait until I finish. Wait until I finish. You don't have to ask question. I'm not allowing question now. You have to listen to me. I'm not allowing question, period. Listen to me. I'm not allowing questions. Please listen. Please listen. So every point during that journey, the air is two parts. One part that is still hot, and then part that already get mixed with the coin, right? And so, what is the implication of this? What is, please stop. So at every moment, you are always between those two extremes. And so if you really want to get that cold, you better make your cooling coil even colder than that temperature. So that adds extra cooling requirement for the cooling coil, right? Because not only you want to hit the target temperature, but you want to even get smaller than it. Does this make sense? Good. All right. So we will add all those sensible cooling and heating loads, latent and sensible cooling loads. And then once we figure out what is our target, we better make our cooling coil even colder than this. Okay. There is one software that will make our life really easy. And I think some of you might have used it in other courses called EASE. Who have seen EASE or use it before? Raise your hand. Okay, one person. So this software is really good. He does not run on Mac. That's the only bad thing about it. But if you have a Mac, then you can just log into one of those virtual machines, which will make you set on an actual Mac, sorry, an actual PC somewhere in the seat lab. So where is my virtual machine? This one. So if I click here, then I can log to a machine in the College of Engineering in Stillwater, right? And I just click here, double click. Maybe problem with Zoom. But anyway, once you are in, you will be able to see the hard disk over there, and you can run the Windows machine. And so in that Windows machine, like here, it's running. So you can actually run EASE. You guys cannot see it. I don't know why. But anyway, so this is the software, and it's actually very convenient because it has the thermal properties of a lot of refrigerants. So a lot of refrigerant are already built in. So it's like, you know, X-Team on steroid, basically. All the refrigerant you want. And it can plot all those pH diagram and all those TS diagram as well for you. Okay. So, and what's also nice about it, it's nice and bad at the same time, is that you can throw a bunch of equation on it. 5 equation and 5 unknown. That could be really useful for us in the 3rd project and 4th project. We will have, as you have seen in the homework, we needed, like not homework 4, but homework 3, when I told you write the equation for the mechanical vapor compression. Well, next time I will tell you, well, solve those equations to figure out what the system do. Figure out how much kilowatt hour he's using to get 1 meter cube of water. So what's nice about EASE is you're gonna throw a bunch of equation on him in any order you want, as long as there is 4 equations, 4 unknown, and he will solve them for you. You don't have to give them in order. You don't have to tell him, use the first equation to calculate work and then use the second one to calculate delta H. No, You just throw the 4 equation, he solved them implicitly with each other, and he give you the 4 variable. Of course, you have to have unknown equal exactly number of equation. There is no running around this fact. But the fact that the convenience is that they could be implicit. The y and x's, the work compressor and H2, the known that you're trying to solve for could be all over the place, and he will figure out how to do it. Okay, so those are just few pages about how you can set the units, and the plots, I find them very useful. So you can just tell him property plot, and you can tell him whether you want pH diagram or TS diagram, and you can figure any refrigerant that you want, and he will do that for you. Okay. So a few things about refrigerant. So we quantify the refrigerant in terms of their harm to the what? To the ozone, to the global warming. So each one of the refrigerant basically get a grade depending on how horrible it is to the environment, right? And so right now, I mean, we moved from the ozone. The ozone depleting potential, those are bad, right? You cannot really find them and you cannot use them that much. But now the next move is basically the global warming potential. So in order to get rid of this R11 and R12 and R22 and stuff, we moved to the R134. But it turned that R134 that we use in old cars, it's actually very bad for the global warming. So that's why the move now is like we need to find a replacement for 134 because it's basically make the environment really hot. So you will see them comparing the different refrigerant basically on graphs like this. Okay, and that will tell you what is their safety, what's their energy efficiency. So the energy efficiency has to do with the shape of the curve on the beach diagram. So if it's not wide enough, then you may be spending a lot of work and getting very little QH and QL, right? So that's the energy efficiency, but you need to think about the ozone layer, right? So you can see how R22 was basically really horrible and how 134 is really good, right? But then it's the global warming now that is a problem for us. So those are the current, and the obsolete is the one that we used to use when I was a student, but we don't use them anymore. And now we are using those guys, 410 and 134, right? And then maybe, and of course, ammonia, we use ammonia too. So it's this global warming potential that is basically a problem right now. And you can see how the 134 is actually not that great. The other thing we talked about, I showed you the slide before, right? And that is that the plan for reducing the omega, the plan for reducing the moisture content is go all the way up till here. You point cool to a really cold temperature, and we said right now that it will be even colder because of the air that leave in between and doesn't get cool. And then now the air is so cold, we basically have to heat so that it's ready for the people. And so what the Department of Energy is trying to figure out now is how we can remove that moisture content by, rather than this long route, by actually going this route. Going directly down and then just cooling a little bit, rather than cooling really, really cold, spending a lot of energy and then heating, right? So this is specifically problematic when what happened? When W1 and W2 were huge, big difference between W1 and W2, right? So when there's a big difference between W1 and W2, then this will have to go very cold, and then the electricity would be enormous. And think about places like this, indoor swimming pool, Jenks Aquarium, like all those places that have a lot of water, that is a big load to climb up, right? So what they're trying to do is to figure out a way to just get the water vapor without cooling. Just go down. The way to go down is just drop your water vapor. How would you drop your water vapor? You will just, maybe you have to send the air into something that just suck water vapor out of it without cooling. Maybe a material that is, you know, those silica thing that they put them in new shoes and new electronics box. Maybe something like this that will absorb the moisture. But then the problem is you have to keep using it. So once you absorb the water, now you need to take those solid particles somewhere else, outside, let them release the water moisture so that they are regenerated. And then you take them back again into the place where they are going to do the job and absorb the water from you. So a cycle where you absorb the water vapor, regenerate the water vapor. And there is a lot of invention and, you know, innovation in that field. Okay, tons of cycles that basically allow people to have humidity control in a smart way. Okay, makes sense? So you can also see how people, one of the challenges they do is that big delta T that you could have in cold environment, when your TH is so high and T low is so low, and the COP of the heat pump will be really, really bad. So what do? They do things like this. If you look at those things, this is research that is currently going on. So I got the slides while I was listening for the Department of Energy basically be reviewed. They show us the proposal they are funded, and they ask the community for their feedback. And each one of those projects is funded by like $750,000 or something, so that they can figure out if there is a way to improve the efficiency. And you can see what they are doing, right? They realize that if they go down like this, their COP is going to really suffer. So what they do is they try to go to the left. So once you come over here, you go to the left, and you can see how they are doing it. But it's basically about separating the liquid and the vapor. Take the liquid, continue down, take the vapor, and then that vapor can actually go and help the compression. Note also that if you compress all the way up till here, that's a lot of work. How do we reduce the compressor work? Intercooling. What's intercooling? You compress a little bit, and then you cool it, and then you compress again. Surprisingly or not, this is actually less work than compressing all the way. Okay? So what I'm saying is that I'm going to plot a compression on a TS diagram. This is the high pressure, this is the low pressure. High pressure, low pressure. So rather than going up like this, and that's the isentropic work, and the real work would be like this, you only go up till here, and then you cool. I mean, ideally, you can cool down to this, right? And then you compress. So this plus this, believe it or not, is less than this. Okay? And of course, if you want to capitalize on this idea, I would say, why only 2 stages? Why don't I do, you know, 3 stages and 4 stages intercooling? Like compress, cool, compress, cool, compress, cool, right? And when you does this, when you keep doing this until you hit this place, now you are approaching the dream for compression. What is the dream for compression? What do you call that compression? It's going at the same temperature. So that's called isothermal compression. Compression without raising the temperature of the air. So you would think it's a longer route, but actually this is the lowest work. Rather than going this route, or even going this route, which is isentropic. So I guess up to this moment, you would always think isentropic is the best ever in anything, not in compression. In compression, isothermal, going this way is the best compression. Okay? And so this would require multiple staging, right? Like that, there's a lot of metal, a lot of heat exchanger surface area to cool, right? But they are trying to do it by, by realizing that, man, I have some refrigerant here. I can put refrigerant, right? And I can help cool like this guy. They are mixing the air once they finish compression here at 8, look at 8 here and 8 here. They are mixing it with 13. That's 13. And 8 and 13 come together and become 14. So compressing 14 is way better than compressing 8. Compressing 14 is way better than 8. Okay, that's what but they did this intercooling without an actual heat exchanger, just by mixing refrigerant from the middle cycle. Okay, so point is there's a lot of ideas that basically try to improve the mechanical vapor compression that we are traditionally have been used. One is by trying to help it get out the latent load by something else, right? Tons of idea in this place. And the second is also by trying to cool it in the middle, right? And there is also, I mean, look at this, where they try to say, that hot air before, that is very hot air leaving the compressor. Rather than just heat the backyard in the summer, backyard does not need heating in the summer, right? Why do I send, 100 degrees C vapor there? Maybe the 100 degrees C should be sent instead to my dishwasher in the water heater. So even in the summer, we need hot water for some stuff, right? So they are basically saying the compressor needs first to get cooled by the water heater, and then whatever is left after he did this, then he can go and get cooled by the outside air. So the point is that don't use something very hot, like the compressor outlet, to cool something not that hot. That big temperature difference is always a bad thing in thermodynamics, right? So we always try to find something else worse, heating rather than the outside environment. Very good. So let's take a 10 minutes break now, and then we will do the project and the homework solution, right? And then we'll have your quiz. So 10 minutes break until 7 o'clock.
Question.
Yes, come, go ahead.
Did you say one moment?
No, go ahead.
Okay. On the example for needing to find an alternative. Yep, right there. The old route, 1, 2, 3. We just passed it on that. Right there. Yeah. The 0, 1, 2, 3.
Why do they heat from 2 to 3?
Why can you not just lower the mass flow rate of the cold air coming in, and then heat with the super cool air? You say that air at
Right. You are basically saying, that cold air, we can just send it to them very, very small.
Yeah.
Right. I mean, that is a solution, but not that also this. So the air that you're going to introduce, he will have, once you go into that place, hospital, classroom, he has a pass that he will go for. And you want him to hit at the end, at the exit. So if that pass is or the tilt is such that, it's like this, maybe like this, maybe it's C. They will end up here. And you rather, and they want to be like here.
I see.
Right?
Yeah.
But that is, you are actually touching in something that they actually kind of like use. It's like mixing. Why don't you mix this with some of the exhausts of the return air and come in the middle somewhere, right? And
moisture control though, right? Because you're gonna end up more.
yes, a little, right, yes. But also what they do is that they will take that heating from this cooling. Like, for example, that can be heated by cooling this, right?
Yeah.
Or like at least heat this by cooling this.
Is it
So
not-
this is for free. So like some kind of heat exchanger where you don't spend electric power in heating and you don't spend electric power in cooling. Let this guy cool this guy, right?
Yeah.
Will you make these solutions available on Canvas?
Yes, I'm gonna upload.
I can't write fast enough.
I know, I realize that. Yes. Yes, fortunately, the homework for the solution is just like 2 equations, but I'm gonna upload the MATLAB file for you.
Yeah, I think I did 4 okay. I'm more concerned about the project.
Yes, let's go through it.
We emailed
Saqib,
and, Saqib today, and Steve couldn't really help where I went wrong. We were about to come get you, but then we realized that we were late in the day. Impressive.
actually the project is very simple. You will see.
Oh, I believe it.
My expectation is very little actually.
We're very close. just don't know. When I'm doing it wrong. We still have 3 days.
All right, I think we should start so that we can have time for your quiz. So next week there will be the exam, but also there will be a homework. And the reason why there will be a homework is just I want to have 25 homework so that every homework is only 1%. Make the calculation easy. But I'm going to make it useful homework.
Wait, say that again?
I want to have a total of 25 homework and quizzes. And so if I don't give you homework next week, there will be only 24 homework and quizzes, not 25. I'm going to have 25 so that it's that I'm going to already give. By the way, a lot of people said like they have problem with sometime, you know, someone gets sick, they get sick. And the question is like, what happened to the project? I am going to waive one project at the end of the year. By waiving, I mean, I'm going to take your lowest and put it all the way up to 100%. So even if you didn't submit one project, if this was your lowest, I'm going to take it all the way up. So you can get sick or have an accident or go to the emergency room for 1 week, but not 2 weeks. 2 weeks, you have a problem. But 1 week, you can get seriously sick for 1 week. And we're going to waive 2 homeworks and 2 quizzes, right? So, but there is something nice about the mess of having a total of 25 homework and quizzes. That's why. So, but I'll make the homework useful, you know, like something relevant to the exam so that you are practicing for the exam. Okay, so now the project. So this project is 5%. All projects, the plan is to have them like 5%. So they're small and light. They are not supposed to be really that hard. Okay, at least not now, maybe at the end. This is a very simple project. And as we said before, the whole idea is in this project is the red cycle. The red cycle, that's what we are designing. I mean, we are not designing this, right? I mean, those were the homework actually. This part and this part, that was homework 4. That's why I give you the homework so that you can realize, you know, how much water is coming out from this and how much cooling does it take to do that. That's the idea behind homework 4. And actually, why don't we do homework 4 first before we continue so that we understand this part, right? So homework 4.1, he just wants you to compare the economical impact of something like this, vapor compression and humidification cycle. The vapor compression, it's like when I asked, you know, my graduate students to actually figure out what is the price. By price, I mean kilowatt hour per meter cube, the energy cost, basically. How much energy does this compressor take to run that vapor compression cycle? That vapor compression cycle is doing what? Is doing the evaporation. It's taking the liquid from here, turning into a vapor, and that vapor go into the compressor, become superheated, right? And then they use that superheated vapor to boil the next stage, right? Then we did this before in the previous thing. Well, the problem with calculating the kilowatt hour meter cube is it has to do with how much you are recovering from the water. Are you recovering 100%? Is that chemical? Are you trying to get just salt sitting at the back? Or you're only doing 10%? How much chemicals are there, right? So it has to do with the concentration of the liquid that you are treating. So that's why this is called wastewater treatment, not desalination. Like you can throw any bad stuff in here and he will just get the water vapor out of it and concentrate the brine. So it's smaller and easier to manage than the rest, right? The humidification cycle, people are trying to do this for produced water. They do humidification, they let the water basically turn into vapor, and then they take the vapor and throw it on the other side and condense it and make it water. And the bad water will basically just come down, hopefully concentrated, right? So the point is to get a journal article. What is the best place to get journal articles? The library. Google Scholar is a good place, but the library, right? The library database, and you go to, I guess, Scopus, right? And you search for, say, mechanical vapor compression desalination, and you get tons of paper, and some of them you can see here say, oh, so you get the article. Like we have a subscription to this. We can get this one. See, indirect mechanical heat pump assisted humidification desalination system. That is, like he's using MVC to help the HDH, right? And so you can click, and sometimes it's available online, sometimes it's not, and then you ask for interlibrary loan. The interlibrary loan is like a form you fill online, and the paper, wherever it is, come to you within 2 weeks max, or even 1 week. They will find out wherever library is, and they will get it. Okay. So if it's available online, you just click on it, and the article will show up. So I would like to make it, or I'd like you to realize, you know, the difference between a journal article and a web page for a company. A web page from a company can claim anything. The company can say, we have the best desalination system ever, you know, but when it's like a journal article, usually it gets reviewed like a lot, right? And so people basically make sure that it's correct, or there is evidence for what they are claiming. So it carry more weight, right, than regular paper. I guess we didn't get good luck for this one. Solar-driven mechanical vapor desalination system with non-filtration. So you will keep searching until you find a paper that actually have the cost, right? And so here, this is a great journal, desalination. What better place to look? And then you find your thingy, right? I mean, there's a lot of them. And maybe here, this one. When you download PDF, and the paper will show up. And then you look careful, like through the figures, and you find out if they have here all the equation to model the system. But what we are after is, do we have kilowatt hour? Look at this. Exergy destruction for each component. He's comparing different mechanical vapor compression. RO stands for reverse osmosis. That's what people usually use for desalinating water. But, and here is the cost, but I don't see different technique. Basic MVC against humidification. So what I will do, I will go until I find the right paper for me, right? But the point is, they are all journal articles. And so hopefully you guys landed on a journal article that have this comparison, right? And we'll show you which one is more efficient. So it's not just the kilowatt hour per meter cube, but it's also what kind of water they are dealing with. So when it comes to produced water that we have in Oklahoma, that's coming from oil and gas, this is usually 10 times more salty than the seawater. Right? So where reverse osmosis is the standard for people just getting water from the sea, trying to get drinking water out of it, if we are dealing with like industrial waste or like, reduced water coming from oil and gas, usually reverse osmosis will not work, will not survive. You will have to replace the membrane all the time. So something thermal like this or this could actually be more convenient to use. And it could be economically low. All right. Second problem, moist air at 50 degrees and 90 relative humidity enter a dehumidifier operating at steady state. Volumetric rate is this much. And the moist air pass over a cooling coil and water vapor condensate exit at 10 degrees C. So the water leaving here is at 10. Saturated moist air exit in a separate stream. We now know that it's not going to be saturated. It's going to be a little bit close to saturated, but not going to be saturated. There is no significant loss of energy by heat transfer to surrounding, meaning that it's just the water and the air. There is no one else. There is no leakage to the outside. Okay. The rate at which the water is condensed in kilogram per minute and the required refrigeration capacity in ton. What is the refrigeration capacity? That Q that the coil is pulling. Yes, the coil is having seawater inside, but it wouldn't matter whether he has refrigerant or cold water. That's still called the cooling capacity. How much heat he's absorbing from that room. So when it comes to how much m dot water falling down, what should we do? M dot air times W1 minus W2, right? So you can see here, I'm trying to get W1 and W2. And do I know the temperature and the phi? Yes, I know, both scenarios, and the pressure. So I use this line, I get W1 and W2, right? Then the m dot water will be m dot air multiplied by W1 times W2, right? So what's missing in here is to multiply that m air with the m ratio, which I did. This is 4.3, maybe 4.2 I did. 4.2. So 4.2 m water is m ratio times m air. And to get m air, remember this was the cubic feet, right? It was cubic feet per minute. What we needed is the is the kilogram per minute. So I need to divide over the specific volume. And I get the specific volume from the psychrometric chart. Just like I got my W1, I can also get my V1, specific volume, right? So this line will give you M air, and this line that you just have to add this line. It's M ratio times M air, and that will be kilogram per minute. And when it comes to how much is the refrigeration capacity, that is the first law. Q is M air, H2 minus H1. Right? Plus how much water is leaving. So basically what we are saying is that the cooling that happened to the air is basically absorbed in two ways: water and refrigeration. The water that condensed, that is an exit, and refrigeration, right? And this is just the conversion at the end to get it in ton. So 1 ton is basically 3.5 kilowatt. So then this is kilojoule per minute. You divide over 60 to make it kilojoule per second. And kilojoule per second is kilowatt. You divide over 3.5 and you get it in Q ton. So just mass flow rate and first law of thermodynamics. Make sense? So air drop his humidity, and that's what you get, the m dot water, and you do this by cooling it from H1 to H2. Make sense? All right. Third problem, I guess, is the humidifier, the place where the air gets super humid. And how does this work? By throwing stuff on him. You can throw two things on him. You can throw water and you can throw steam, vapor, right? So how does this affect things? If the air is over here and you throw water on him, he will go up like this, right? That's the evaporative cooling part. But if I throw steam on him, he can go like this. Not only his W2 or omega 2 will be bigger than omega 1, but look at that. His T2 will be bigger than T1. Why? Because the H that you are throwing, rather than H saturated liquid, it will be H vapor. That's a lot of H. So the big H, the steam that you're gonna throw, can take you not only adding water vapor, but even heating the air. Okay, so the problem statement said you are throwing steam on him. Okay, so how do I generate steam? I thought that was water, seawater, hot seawater, but water, right? So if we are plotting the TS diagram, and this water is like really hot, like maybe, I don't know, 90 degree hot, but also, so let's make it 100 degree hot water. How come it's not vapor? How is it 100 degree and it's still liquid? Why is that? Because for 100 degree water to be vapor, you need be ambient, right? You need the atmosphere. You need the 101.325. But you can be 100 degree and you're still water. You can be 200 degree and still water. Why? Because your pressure is higher, right? So those are really high pressure. Yes? So if I take that guy and suddenly lower it to a lower pressure, what will happen? He will, that's throttling, he will flash. Flash meaning that, so this is 0.1 and this is 0.2. So he could have HF and HG. He will go here and here. Of course, the amount of m dot steam that will come out is smaller than the total mass flow rate. Only one part, like small part, become steam. How much is that part? M dot steam is going to be X2 times M dot 1. M dot 1 is that hot water that is coming here, and X2 is the quality of this point. And obviously, the lower I take it, the lower the pressure in that humidification place, the more the part that become vapor, become steam, and this become liquid. When you take 4263 energy conversion next semester, you will see we do this all the time when we have hot brine coming from the ground and we need the steam to turn a turbine. So yes, good for us, hot liquid, but I cannot, I'm gonna put it in the hose and shoot it on the turbine. No, I need steam. So we flash, we reduce the pressure and steam will show up. Little steam, but some steam will show up. Okay, so back to the problem statement, you know, the problem doesn't tell you to design the whole system. It just said here, saturated water vapor at 90 degrees. So at 90 degrees, saturated vapor. So that must came from a liquid that was even hotter than 90 degrees. So that when you flash it, he dropped to 90 degrees. Some vapor and some liquid at 90 degrees. Okay, and you shouldn't, if you're like wondering, like, is that black magic? How did the vapor come from? Who's paying? Who's paying for all that Hg? Because Hg is how much? Of order of 2,000 kilojoule per kilogram compared to HF, the liquid side, it's of order of what, like 200? So who's paying for that 2,000? You know, that make you vapor? Who's paying for this guy?
The compressor?
The compressor, no. It's this. It's the fact that this H dropped to this. Like rather than everyone at 100, now we are sitting at 90. That drop allowed the transfer of joules from here to here. And because there is not that many steam masses, that allow that small minority, because that X is like in the middle here, it's like 0.1, 0.2, it's not 0.5. We're not going to go all the way to the middle. So that 10% got really a boost of enthalpy because those guys are paying for the reduction in H. So rather than we are everyone here sitting at say 300, but that was 300 kilojoule per kilogram. That was a lot of them. Now we have the majority is sitting at 250 kilojoule per kilogram, but then 10% of us end up become vapor, right? So someone is paying, and that is the reduction from the high temperature to the low temperature. Of course, now this water at 100 degrees C, how did it happen? The mechanical vapor compression cycle. The condenser that was heating the water, you need to take it up to high temperature so that when you flash it, you become liquid and vapor at decent temperature. Okay? So back again to the problem at hand here. So he's basically saying, I am just throwing on you water, saturated water vapor at 90 degrees. And here is the flow rate. That 18 kilogram per minute is not the total water. It's part of it that become vapor. That steam now going into air, what is the chances that he's gonna condense? He's gonna probably move in the air and become moist air because it's already, you're throwing steam already, you're throwing water vapor, right? It's like you're cooking dinner and this is the plume coming up from the rice cooker. I mean, what will happen to it? It will just mix with the air in the kitchen and the air become a little bit more moist, right? So yes, absolutely, it will get absorbed basically in the air. So it's injected into the mixture at a rate of this. There is no heat transfer to the surrounding, and the pressure is constant throughout at 1 bar, calculate the exit humidity ratio. You want W2, and he want the exit dry bulb temperature. So that tell me mass conservation, energy conservation, right? And you can see the solution is actually here. So that homework was just like write the code, run it, get the answer, right? So what is going on? He say, I know what's happening at 60 and 50, right? 60 and 50. And so that allowed me to calculate W1, right? And so if I know W1, I use the conservation of mass, which say the extra m dot water is going to be W2 minus W1 multiplied by m dot air. We have used this before many times. Make sense? So you got yourself W2. And when it comes to the energy, what's H2? This, the first low thermodynamic. The new H is the old H plus how much energy did you blow on me? It's H water times W minus W. And that H water is saturated vapor at 90. Okay? So now what do I have at 2? I actually have H2 and I have W2. So if I have H2 and W2, I can go ahead and read what he wants, which is what's the temperature at the exit, right? The exit humidity ratio, sorry, W2, and what is the dry bulb temperature at the exit, which is T2. So I got the temperature and I got the exit humidity. Make sense? And I'm gonna post that code for you guys so that you can see it, right? But it's simply, you know, the two equations that I told you, mass and energy, right? And he get T2 and W2. And before we just give him the m dot air and m dot steam. Ouch. I shouldn't see it there. Yes. Yeah, it didn't, because that's excellent point, because this problem statement does not talk about any other water. If we get in project 3 or 4 modeling the whole system, then you will. But this problem statement, when you read it like this, was m dot steam thrown out on the air and the air get hot. Okay, so now what happened to the actual water that does not get boiled into vapor and it just remain as hot water? Well, if you read this problem, that's what I just made this problem so that you can patch together what's happening in the big cycle for the project, so that you understand. Not that you need to understand, you can design the project, solve the project without understanding the whole system. But look at this, the air is coming with 60 degrees. What? How did the air come at 60 degrees? I thought that the air left that chamber, the dehumidification chamber, at what temperature? If we go up here, it left at 10 degrees. So the air was leaving at 10. How does it meet the vapor or the steam at 60? No, the condenser is not there. The condenser is talking about the water. I'm talking about this air coming here at 10, and then go and meet the steam at 60. How did that air at 10 meet the steam at 60 and leave as moist air at 90? What happened in that place? The water that is coming at 90 trickle down, while the air that's coming at 10 trickle up, and they pass through each other, and the air get heated to 60 while the water is. So the hot water is heating the air, and then the hot steam take the air from 60 all the way to 90, right? And while he's doing this, he's also adding his W, right? So this is kind of like 2-stage. You take the air up. Why you're heating the air? What's the point? You're heating the air because he become more hungry for water vapor. If you take him hot and hot, there is more room, right? More room for omega, right? If I just bring him at 10, he will not carry that much water, but I need to bring him at 60 and even add more, right? So that he can absorb as much water vapor as possible. So what I'm saying is, if I'm coming here at 10 degree, right? And what he said, like 100% or even 90% moist, then what we need to do, sensible heating. And then until what, 60 degree. And then with a steam, take them all the way up to 90 and very high humidity, right? So the reason why you are adding very hot steam, H vapor, is that you want the curve to be like this, rather than going up like this, or even worse like this. If we just put cold water on him, we are trying to let him go in that direction so that we can reach really big omega. So you can see that it's that difference between the 10 degrees C and between the 90 degree. It's that difference that give you big omega 2 minus omega 1. That's how this cycle is efficient. We can carry a lot of water in the air between the two chambers. That's our carrier. And to make them carry more, I need to go cold here and I need to go hot here to give myself room to add more humidity, right? So the homework is a piece of cake because the equations are in front of you, okay? And all you need is just maybe add the numbers, but just run the code, right? So I'm thinking something similar for the next homework, just that you can get more comfortable with MATLAB, and then you will be able later to use it for your own design, for something like really heavy. Okay, but think of this as just training. My only purpose is that for you to understand how does this file work, what we give him as an input, and how this is output. By looking at this, you figure what's input and what's output in MATLAB. Specifically those charts. Okay, now the project. So now we understand that this two-chamber load air with water, drop the water from air. Load air with water, drop, right? And as he stated here, the purpose of this cycle is, or your job is to cool and heat the air to, he said, 15 degree and 60 degree. You want the air in this chamber to be 60 and here to be 15, okay? So how we grade our project, what's required? The problem statement. The problem statement is to say those numbers, to say 15 and 60. We are building a cycle or designing basically a mechanical vapor compression cycle to do that job, take you from 15 to 60, okay? And maybe something along like why, maybe you're saying, that's because we want to, the big picture is that we want to condense air from W1 to W2, and that allows us to get m dot water, right? That is what I need from the problem statement. Number that I'm giving to you, big picture, what's happening. You get your 4. Okay. Second part is the requirement development. The things that you need, number that you need in your solution that the customer didn't provide because the customer does not know how to do it. You just want the air to be 15 and 60. But the mechanical vapor compression cycle need B saturation. We need B high and B low, so I can figure out what is the work of the compressor and calculate the COP for you, right? So you need to provide those numbers. So that's when you're gonna bring those numbers from physics, like what physics? Like for example, you want to cool the air from 60 to 15, then you must be using something colder than 15, right? Maybe the seawater need to be 5 or 10. So I was telling Saqib today that, you know, if they pick 5 or 4 or 3, that's okay. Don't make them lose points. But if they pick 0, they lose points. 0 what? 0 difference. If you say you want to heat the air, cool the air to 15, then use 15-degree seawater for that. You should lose points because you don't understand the physics of how you can cool something. You want to cool something, you better be colder than it. Otherwise, if delta T is 0, how much is the area that you need to do that? How much? Yeah, UA delta T, the one equation that we learned from the heat transfer course. If this is 0, this has to be infinite. Okay? It's not gonna work. So you have to do this something, maybe 5 degrees, 3 degrees. You need to tell them I need to be cooler. Okay? Okay, so the seawater will have to be colder than the air, maybe 10. And on the other side too, the seawater need to be hotter than the air, the 60. So although he's doing it from 50 to 60, you on the other hand need to be higher and lower than 15 and 60, right? Seawater need to be higher and lower than 15 and 60. Now, that seawater that's gonna be colder than 15, which let's call it 10, how it's gonna get to 10? Actually, you're gonna bring the seawater from the sea, which is sitting at room temperature, say 25, and then you're gonna cool it by 10. So how cold is the refrigerant that will make the seawater go to 10? Probably lower. Maybe the refrigerant need to actually work at 5 or something lower. So you would say, well, I need to have refrigerant that's 5 so that he can cool the water to 10 so that it can cool the air to 15. So you would say here, this is the requirement. You know, like the customer should have said, you need a refrigerant that goes all the way to 5. And that part about 60, you know, is that true that we need to heat the, we need to heat it to 60. So how hot? So the question is, I mean, obviously, this is the hot part of the cycle. This is the mechanical vapor compression, right? And we said refrigerant set at 5 degrees in the evaporator. How hot it should be at the condenser? How hot to heat air to 60 degrees? That's the seawater at 65, right? The seawater need to go to 65. So maybe this guy need to be to 70, right? Problem is, if I look to those refrigerants, you know, that is like really, I mean, they don't go that hot. You will have very little choices. What's 150 Fahrenheit in degree C? So 150 minus 30, that is 120 divided by, multiplied by 5/9, that's roughly 60. So this guy finished here at 60. Okay, so the question for you is, do I really need this to be at 60 to heat the water to 60, or I can be at 45 or 50 and still heat the water at 60? Is that even possible? This guy is sitting at this T saturation for that refrigerant is at 55 and it still can heat the water to 60. Is that possible? If you, it's actually this part, not subcooled, but it's this, it's the superheating part. So on those graphs, the compressor does not deliver you here. The compressor delivers you because of the fact that it's isentropic. He delivers you up here. What's up here? That is, you know, 10 degrees hotter than this, or even more, right? So what I'm saying is there is room Again, I'm going to post all this for you. There is room for the water to go up, not just T saturation, to go up above T saturation. It could actually end up being like this. You know, this could be at 60 and the water will go up even more. When did we see this? Where did we see this before? Where the steam heating something under him managed to make it hotter than him. You have seen this before in the feed water heater, in the Rankine cycle. And we actually have a term for this. When the exit water is hotter than T condensation. And we call it terminal temperature difference. And I told you that when you look at this big Rankine cycle that we had from Jenks, the terminal temperature difference could be negative, meaning that the liquid leaving is hotter than the steam condensing because the steam come superheated. Okay, so while the steam is doing this, you can take, especially if it's counterflow, then the liquid can really go up. So I guess what I'm saying is you can afford for this to be at the desired temperature. So if you want the seawater to be at 80, you can afford to make it at 80. Why? And then all this argument about like you need infinite area. No, you don't need infinite area. You still have a superheater. That steam will condense while he's going to take your water to a higher level. And those double counterflow heat exchanger do exist, and they are very cheap actually. And I mean, before COVID, we used to go to our plants, and you will find on the shelf, you know, they have a lot of those counterflow heat exchanger cubes. They will what do they look like? Yeah, like this. So you can see how they don't take that much space, and there's one inlet, and here's the exit. And on the other side, the same thing. So you send the hot fluid in the middle, the one closer to the ambient on the outside, and they hang around in a counterflow. Of course, inlet and outlet, right? So that they are counterflow. And so when you do this, then you are guaranteed to basically be able to do this part. Of course, this part here, you need to make sure that this part is still greater than 0. They call this the pinch point. It's as if that it's gonna pinch the temperature. So you need to make sure that this guy remains. So this gives you some room here. The T saturation for the condenser doesn't have to be that hot because thanks to the superheater. Okay, so, and also what else you can add in this section? Maybe you could say, what kind of refrigerant? He didn't say what kind of refrigerant he should use. Maybe you tell yourself, regulation tell me I shouldn't kill the ozone so that we all don't get skin cancer. So R12, R22, R11, all those are basically, I'm not even going to consider them. I'm only going to consider, you know, good refrigerant that have no ozone danger or risk. Maybe you can even take global warming, you know, refrigerant that even restrict you more. But in that task 2 is where you bring standards, you bring stuff where you would basically say, I'm gonna, here's my space domain. You're limiting yourself. This temperature, that refrigerant, okay? And so in task 3, then you will take whatever refrigerant you picked, you get the H's, right? You put them here and you calculate the COP. Now, we had a lot of questions. So we talk about task 1, 2, and 3. So in task 3, the question is, what is the COP we should use to judge R134 is that choice? That's excellent. So the COP is always output over input. Input is very clear. It's the work compressor. The output is not clear here. And a bunch of you asked about this. And I tried to run away from this because I wanted you to figure out, this is your design objective. You are building your design objective yourself. So in this cycle where our job is to get that range extended. W1 all the way up, W2 all the way down. Do we care about Q dot L or do we care about Q dot H? What is really our goal here? What we are trying to maximize. So we would say this is much better designed than this one. Q dot L here. Q dot H over here. I think it's really, for the lack of a more sophisticated analysis, I wish, like maybe in the next project, that the goal will be to maximize M dot water. But it's very clear to me that M dot water that will drop is proportional to W2 minus W1, or W1 minus W2. That is what make M dot water. So it's really Q dot L plus Q dot H. So what I told Saqib when he's grading is that, I told him, if they hint that I cannot judge by, remember gamma and beta? What's gamma and beta? COB for refrigeration and COB for a heat pump. When it's Q dot L, they call it beta, and when it's Q dot H, they call it gamma. The COB has two symbols. So I told him, if they hint to the fact that I cannot judge based on Q dot L alone, or I cannot judge based on Q dot H alone, I have to consider them together, not maybe adding them, but just like you would say, I'm going to use both of them. This refrigerant makes those two guys perfect. So I'm going to pick him. That is your way to get 4 out of 4. But if you just said Q dot L or Q dot H and you didn't take anything else, that's not the whole answer. That's not really how you can judge whether this is a good design or not. Okay. So what happened in task 4? We wanted to make the calculation now more accurate. This was a draft. This was like a crude calculation, isentropic. And I said, just use, consider efficiency of the compressor and superheating and subcooling. So that is superheating and that is the subcooling. Those things, when they work or when you consider them, they make the COB worse, right? So you want to include them to actually come up with a better estimate of your calculation. So that's the whole design philosophy in this course, is that we want you to come up with a very rough draft, but quick draft. And then you make it a little bit more sophisticated by adding all the peanuts, That the main nuts, the important things was COP on idle cycle. Now you do those things and you see how much does it change. Does it change 5%, 10%? And you do this calculation. Make sense? All right. So now the hard part, the one that always people lose points over, is number 5. Quantitatively assess your assumptions. Any one of those could have been worked if you didn't do them, but I already in task 4, I told you to actually include them. So those cannot be assumption that you didn't assume. Or no, sorry, assumption that you didn't verify, because you already did verify them in 4. So in 5, you have to pick something else that you assumed and you don't feel safe about, and you are trying to quantify, well, is that really too dangerous to assume, or no, it's okay. So what can happen? I would suggest like maybe something about the delta T. Maybe, when you said, I'm going to assume 5-degree delta T between my water and my air, or even if you assumed, like what could really work is that you would say, I'm going to go from 15 to 60. 15, that this thing is 15 to 60. Right? You just said that's my design. But then in 5, you'd say, wait a minute, how could I assume that a 15-degree refrigerant will heat 15-degree seawater that will heat 15-degree air? Let me now calculate how much increased area would I need if I actually have relevant delta T. Right? So you can check the effect of delta T. Maybe you can check that the effect of oil. If you have Googled a little bit, you would find out that all the refrigeration cycle kind of deteriorates if they have oil, and there is oil because the compressor need oiling. and that oil go in the cycle, and that can drop the performance. The H value would be a little bit different. The pressure of the evaporator will be different. So you can find out, well, what is the real pressure now because of that oil? And how does this change my calculation for my HQ.L, for example? So something that you would assume perfect and it's not, and you're worrying about, and you do the calculation here to say that was really dangerous, and that look at the number change a lot, or no, that was very little and I don't see that much, so we are safe. All right, question about the project? Very good. So we are ready for the quiz. And the quiz, I guess you can get it from assignment. If you click to assignment, and it's quiz 6, and it's 2 parts. One part say write for 20%, write whether you are in class or you are on Zoom. And if you're in class, write your seat number or class number so that we can track you in case people get sick. And the second part is they please sketch a real mechanical vapor compression with superheating and subcooling, just like the one that we saw. Superheating before the compressor, subcooling after the condenser. And label them 1, 2, 3, 4. Wait, 1, 2S and 2 and 3, 4. What's 2S and 2? Isentropic compression, real compression. So label them, okay, and plot it on TS and BH. So to reiterate, you want to make a sketch of the cycle. So that's the compressor, condenser, expansion valve, evaporator, and you're going to write on it 1, 2, 3, 4, and then you plot the TS and you plot the BH. Labeling where is 1, 2, 3, 4. Okay, and please use a ruler to make it neat. And if you don't have a ruler, use the edge of your laptop. Right? Make a neat line. I can't hear. You need to write what? No, there is nothing given here, just the sketch. So this problem is all about those 4 states, okay? Plotting them on the BH and plotting them on the TS. And so that's for 80%. So he's going to give you 0.5 point for each one you are locating at right. Remember, the exam is open book, so you can go back to the notes and look to it.
So I understand we've sketched on, or we, to plot the diagram, but
So we are making 3 drawing. We are drawing the sketch where that cycle sketch, which has the compressor, the heat exchanger square, the symbol for the expansion valve, and the square for, or the rectangle for the evaporator. And in that drawing, you're gonna make 1, 2, 3, 4. And then the TS diagram and the BH corresponding to that with the number on them. And let me tell you, when you guys plotted the Rankine cycle, remember the big Rankine cycle was a 4 evaporator? The people did really horrible. I mean, no one, like almost like only 2 people got it perfect out of 55 students. So please do a good job.